All right, so you can hear me, right?
Yes, sir.
Okay, good. All right, so the topic for today is dynamics, right? So let me just get some things ready. Okay, so dynamics. Anyone has any idea of how we started off with physical quantities? That was the first topic, right? And in physical quantities, we saw what do we mean by a physical quantity. We needed something to write down the laws of physics, right? And that was the starting point. So we started off by, I'll just use P and Q for physical quantities. We needed these to write down laws of nature, right? And now having something, having some quantities that I can use to write down the physical laws, we started off our discussion with the very basic thing that was kinematics, right? Kinematics. And kinematics was the study of motion, right? Without considering or without caring about really of any forces or anything for that matter that might have started or caused the motion, right? So it was we used physical quantities to write down laws of motion. Well, not Newton's laws of motion. We'll be writing those in this dynamics. While laws of motion is a very general statement that uh, physical quantities are there to write down the laws of physics, right? So one of the things for physics, we're writing down how would we describe motion, right? So writing down the laws of motion without any considering any acceleration or whatsoever. So that was kinematics. We did not care about forces at that time, which leads us to understanding another thing, that is dynamics, which is the goal of this chapter. And here we will see, okay, something was moving, all right, but what caused that motion? What was the what was the essence of that motion, right? So here we want to see what caused the motion. That's what we want to study in dynamics. So is that clear for everyone? Are you following along? Is everyone following along?
Yes, sir.
Clear.
Yeah. All right.
Yes, sir.
Okay, good. Okay, so let's start like this. What do you think? Anyone can tell me what would be something that would cause a motion? That thing happens and the result of that is motion.
Me. I can cause motion.
Yeah, of course. Yeah. Okay. What would you be doing to produce, any translational or displacement? Just give me an example.
Push.
Like applying
Push.
a force.
Yeah, a push or applying a force, right? So, for example, you have to move a block. You're going to push this block, and that push is what is called a force. You could also do something else. You could pull this block, and that would also be a force, right? The only difference between push or a pull is direction, right? So push is one direction, pull is the other direction. So really, you should think of these two things in terms of just directions, nothing else, right? So you can then say that if I am pushing something, just say that that's positive. Assign a signature to that. And pulling it, assign a negative signature to that. That's completely on you, right? Here we are going through some of the things that we had also discussed in physical quantities, right? Because we discussed forces in physical quantities. Anyone remembers?
Yes, I have some idea.
Yeah. Okay. So, but we'll go through these things, forces and all of them in details. Okay. So push or pull, right? these are the only two things which I can do to this box. Okay, maybe I can apply this push or pull from this direction. Maybe I can apply push or pull from this direction, right? Push or pull from this direction, push or pull from this. So we have infinitely many directions, really, if you think about it. So, but you can only do two things. You can push or pull. And that's why the method of signatures is handy in defining the direction, because there are only two possible directions in very general sense, right? You can either push or pull. So you can say that push is positive, pull is negative. I could have went in a different way and say that pull is positive and push is negative. It's the same thing. You just have to follow along a particular convention that you set in the beginning. All right. So that's how you can cause motion. So of course, for example, I push this block. What happens is you'll observe that it starts moving, and maybe it might come over here and stop, right? And so I have produced motion. So that is a force, right? Now, a force can be of different forms. You can apply a force. You can apply a force to start the motion, or you can apply a force to stop a motion, right? Which also means that I can apply force to speed up something that is already moving. So suppose that you roll a ball, right? It's rolling, or just consider for now it's translationally moving along a line, and it's already moving, and then you just, something triggers you, and you just decide to kick this ball anyways, right? It's already moving, you decide to kick it. What will happen? You will obviously see that the speed of the ball starts increasing. So what happened is you have caused this ball to accelerate, right? And so what force does is force tries to increase the speed of an object. That's what force does. So maybe something was already at rest, meaning it was not moving, and then you would apply some force to it. It would start moving, right? It would gain some velocity. So it has increased the speed of the object. The other thing could be that, maybe something is already moving and you try to pull it back. So you're trying to reduce the speed, and so it's decelerating, negative acceleration would be there. Motion of the body, right? Okay. So that's force. Now we can have different types of forces. Let's quickly discuss the types of forces now. Is everyone okay with the concept of force now?
Yes.
Yes.
We'll talk more in terms of,
Yes.
How can we use vectors, the vector representation of force. We'll talk about that as well, right? But before we go on to that, let's discuss the types of forces. We can have, really, if you generalize it as much as you can have two types of forces. One is a contact force, and the other one is a non-contact force. All right. So can you give me an example of contact and non-contact forces? The name is very obvious, right? Contact means that there should be, if I have an object, it should be in contact with something, right? So an example is a block on a surface, right? On a straight surface, on a table, for example, right? Or on a ground, there is a ball. So that's also the force. It is a contact force. So for example, you could think of weight. Well, not weight really, but instead the resultant from this weight, which would be the normal force acting on this ball because of the ground, that would be in the upwards direction. So that's a normal reaction force, and we'll discuss those. Can you give me any other example of contact forces? Anyone?
Book sitting on the ground.
Yeah.
Book
Okay.
on the ground.
Right. Exactly. So that's an example of a normal contact force. What could be other types of contact forces? Anyone?
Friction.
Is it me kicking a ball or
Friction.
someone kicking a ball?
Yeah. Yeah. But the answer I was looking for was a friction, for example, is a type of a contact force, right? So we'll talk about friction as well. Another one is tension. Tension is also a contact force. Is I don't think so. You might, all of you might be aware of tension. For example, consider you have this ceiling and you have a string that hangs from the ceiling, and attached to a string could be anything. Suppose it's a ball, a heavy ball, right? Now, of course, the ball has some weight, which would be the mass of the ball times the acceleration due to gravity. That's weight, right? And so that's a force that is acting directly towards the center of the earth, or you can say directly downwards. Now, because this ball is hanging from the string, there will be a force that develops in the string, which would be the tension force, which would always act in the opposite direction to the you can say, not, I cannot say really to the weight, but it would be acting in the opposite direction to the ball, right? So the arrow points in the other way, points always towards the roof or the ceiling. So that's tension. So three types of contact forces are normal contact force, right? Which is, for example, I have a table and I have a book lying on the table, then there will be a normal contact force N on this book, right? So it is really a push of some sort that you can say, which is exerted by this table, right? This table, I ignore my drawing, I can't really draw a table properly, but I think you get the point, right? So this normal force is a force that the table exerts on this book, right? And it is perpendicular to this table. So is that clear? The idea of normal contact force?
Yes.
Yes.
Okay, good. All right. So then the other one is friction. Friction. And we're all aware of friction. It is also one of the reasons that we can move, really. And it is a force that acts on a body which opposes the motion. For example, we discussed air resistance in the last lecture, if you remember. Air resistance was a friction force, right? And in terms of air resistance, the friction was coming from the fact that I have a car which is moving. It has to fight against these air molecules and push these air molecules out of the way. Really, it has to push these air molecules out of the way to move forward. So that was a friction that this car experiences in terms of air resistance. And this friction would be acting in the opposite direction of the motion to slow down the car. Right. Now, another example could be, there are so many examples if you think of, their friction exists everywhere. And the reason for that is because, for example, consider you have two surfaces. Suppose that these are two surfaces. And I want to slide these two surfaces on top of each other, right? So maybe one moves in this way and the other one moves in this way. Now, in a hypothetical situation, it could be that these two surfaces are so smooth that the friction force is zero, right? Now, where does friction comes from? That's what I'm trying to get at, right? The friction comes from the fact that no surface, of course, I'm talking about the friction in terms of surfaces, right, at this point. Now, it comes from the fact that no surface is entirely smooth all across all across its body or whatever, right? No surface is entirely smooth. So for example, if I were to look at this closely, I'll see that the top surface might have some, irregularities, and so would the bottom surface would have some irregularities. So this is the top surface, while this one is the bottom surface. And there would be these irregularities. I can try to make it as smooth as possible. So maybe I would be able to remove some of the irregularities, right? But I could never remove all of the irregularities, no matter how hard I try, right? And so that's why when these irregularities come in contact with each other, right? These two irregularities, they come in contact with each other, they interlock, and that's what produces friction, because that's what's trying to slow down the sliding motion of these two surfaces, right? So that's where friction comes from, really. Then you have tension, and I gave an example for tension already in terms of this pendulum. So is the idea of contact forces clear?
Yes.
Okay, good. All right. Now let's talk about.
Sir, 1 minute. Can you explain me the whole, this area is jagged. So when they connect idea again, because I didn't get it.
No, can you please repeat? I did not understand what you were saying.
Sir, you said that, there was friction pretty much everywhere. And then you proceeded to give an example of how, you can try to cut out this jagged area, but you never can do so. And when they come into contact with each other, I didn't get that.
Oh, okay. So what I was trying to say is, I was really trying to say that where does friction comes from, right? So for example, imagine two surfaces, right? Two surfaces, and you want to slide these two surfaces over each other, right? So suppose that's what you're trying to do. Or maybe say that this surface is at rest, it's not moving, and you try to move this upper surface across this lower surface, right? So that's where you're moving it. What happens is, in reality, when you look at it more deeply, right, you'll see that there are some irregularities, right? There are some bumps on the surface. On both of these surfaces, there are these bumps. So when you look at it as close as possible, right? Now, when you do that, you'll see that these bumps try to, yeah, sorry.
Is the irregularities on the microscopic level, so we can see them normally?
Sorry, I cannot hear you. Can you speak a bit loud?
Is the
your voice is cutting. Is it just me, or is it for everyone? Can anyone understand the question? Can you tell me?
Is the irregularity on a microscopic level?
Yeah, exactly. That's what I was getting at, right? The irregularities, you can look at them at the microscopic level. When you look at the surface so closely, you'll always see that there are some irregularities. You'll never see a surface that is entirely smooth as this line, right? You'll always see, when you look at something as close as possible, you will see these irregularities, right? There will be no surface that is completely smooth all across. So that's what I was saying, right?
In space, there's no friction, as there's no air molecules, right?
I mean, more or less, yeah.
Okay.
You can approximate it to that extent, right? So anyways, answering your question, Hassan, did you ask the question, if I remember?
Yes, yeah, I did.
Yeah, so the answer to your question is that these irregularities, you see these, if I could zoom in, so the idea is this: when you look at something so closely, you see these irregularities and they come into contact with each other, right? So maybe this irregularity will fix inside this hole that would be over here, right? And when it fixes something like this, right? So it fixes inside this hole. So then to push it, you'll have to make this thing move. You'd have to, kind of break this irregularity and then move forward. So in breaking that irregularities, it will try to slow down this sliding motion, right? The motion was in this direction, right? So you'll have to use your imagination, think that there is something when you have, or let me try to draw it something like this, right? So maybe in the bottom surface, there will be an irregularity opened like this. And in the top surface, maybe there will be some irregularity that fits inside this hole, right? So this would fit inside this. And now it would be kind of like an interlock between these two surfaces. So if I still want to slide this, I'd have to break this thing, so that if this thing breaks, then I'll be left with this upper part, and then this would slide along. So in breaking that thing, it is really what is known as friction, right? Which is trying to resist, because of course, in breaking that thing, it will slow down this motion, this one, and that's what friction is. So what it does is friction always opposes the motion, the direction of motion between the surfaces which are in contact. So in this case, the surfaces were these two surfaces, right? Is it any clear?
Clear.
Okay, how about you, Hassan? Is it clear?
Clear.
All right. Okay. So that's more or less contact forces. Now let's talk about something that's a bit more interesting, which are non-contact forces. Well, we're talking in terms of forces right now. Forces is a very outdated word in modern physics. We don't talk in terms of forces because especially the non-contact forces, right? So for example, I'm going to give you an example over here. Let me start with an example that I think everyone would be familiar of, is magnetism, right? Magnetism or magnetic force,
Yes, I am familiar.
Yeah.
I understand
okay. Okay. So what is magnetic force really, in your opinion?
It is
this
field around an object that is negative or positive.
Well, more or less, I'd have to agree with that as well. But you could have given the same definition for electric force or electric field as well, right? And that's not, your misunderstanding. The thing is that magnetic force is a result, or you can say it's magnetic and electric force are the two different sides of a same coin, like heads and tails, right? Now, why do I say that? I'll explain. So magnetic force is, for example, we'll consider a magnet, right? So suppose that you have a magnet, and now suppose you have another magnet. Now, what could happen is, maybe if you have this side and you have this side of this magnet, what happens is maybe they start to come closer to each other and they stick together. This is that you feel a weird feeling when you bring two magnets close to each other. Sometimes you'll see that they'll stick to each other. They'll try to, snap your hands, or I don't know if that's the right word. They'll try to, when you have these two magnets in your hand, you'll feel something that the two magnets are trying to get closer to each other.
You feel that they are attracted to each other.
Yeah, and exactly. So that's the attractive nature of this force. And then if you flip one of the magnets, you might see that these two magnets, all of a sudden now, they're trying to get away from each other. So that's repulsion. They're trying to avoid each other really. And so we can then assign this concept to this thing, that we can say that one is positively charged and the other is negatively charged. And when these two are positive and negative, they'll attract and they'll stick to each other. There is another convention that you use. You say that one is north and one is south pole. So these two are, because these two are exactly the opposite of each other. So again, you can think of these as opposite things, and opposites would stick to each other. And then you suppose you have positive and positive. The idea is like meaning both are of the same type, right? So you have positive and positive charges, or you could say north and north. What happens is they don't like each other. They don't want to be next to each other. So they'll try to move away from each other, right? So that's positive, positive. So the distance between these two magnets have increased. And same is the case for negative as well, if both of them were negative. Now, that's magnetic force. We can go into lots and lots of interesting details of this force really, by the way, but that's not a part of your course. And so I'd just like to tell you something. In the beginning, I said that electric and magnetic force are the two sides of the same coin. So for example, I have electric force here. On the opposite side of this coin, I have magnetic force. And the reason I say that is simply because you'll have to understand relativity, which is nothing but saying that motion is completely relative. There is no such thing as absolute motion. I look at someone that is moving. For example, I'll give you an example, and this would be helpful to you in other things as well, kinematics and so on. So for example, consider that you're standing outside and there's a car that is moving. Suppose the car is moving at some speed, say velocity v, right? Now you're looking at this car, you'd see that the car moves with some velocity v, right? Imagine that there is someone that sits inside this car. For example, now suppose that you're this person who's sitting inside the car. What would you feel your velocity to be?
The person sitting in the car would have no velocity because he's sitting in the car.
According to him, exactly. Yeah. So that's according to him. So let's name these two persons. This is person A. This is person B. Now, B would feel that he's not moving. He's sitting in the car. Obviously, he's not moving. He would say, I'm not moving. So my velocity is 0. But on the same time, if A is looking at B, A would say, bro, is something wrong with you? You're moving with some velocity v. Of course, you're moving with some velocity. But the thing is that physics says both of them are exactly right. So what's the problem then? The problem is there is no problem. The nature of motion is such that it's relative. And I'm going into more details. I'd not like to go into more details. I'll just end this with here that this relative motion is the reason that magnetic force exists. So when you think of something, so for example, if I have a positive charge and it's just sitting over there, it's doing nothing, it's just sitting. At that time, there will be a force that it could experience some force, and that force is the electric force. But suppose that I push this charge and it starts to move now. If this charge starts moving, then this charge would experience magnetic force as well. So that's what I was trying to say, that these both things are the same. So it depends. So maybe for some person, he would say that there is no magnetic force at this point. At this time, there is no magnetic force. But maybe the other person who could see that this charge is moving, he would say that there is magnetic force as well. So both of them would be right, but it depends on the relative motion of this charge. Is there magnetic force or is there no magnetic force? Anyways, that's the idea of magnetic force. It's attractive. So the key points that you should take from this is there are two types of magnetic force: attractive and repulsive. And so if attractive means that there should be always unlike or different charges, different anything, right? So anything that is unlike, it would be attractive, and anything that is the same would be repulsive. Like charges, like poles, North Pole, South, North Pole is like pole, so they would repel, right? Okay, so that's magnetic force. Next, we have electric force, and the idea is still the same. It's now you should know that electric force would be there if there is no motion, right? So you could have a charge that is sitting over here. Suppose this is a positive charge, and now this charge is sitting over here. It is positive, experiences nothing. Of course, now because if it's a positive charge, it will have some field lines, but we'll not talk about that right now. But now suppose that I bring another charge out of nowhere, and suppose that this charge is negative. Then what happens is these two charges will experience a type of force, which is the electrical force, such that the force would be something like this. And the positive charge will feel a force in this direction, and the negative charge feels a force in this direction. And the distance between these two charges, you can just call it some r. And then you can also go ahead and write down an equation that governs this electric forces, right? Which I'll just write it down here, but you don't have to get into any details of it. 4 pi epsilon naught, these two charges, suppose Q1, Q2 divided by r squared. Right now, you don't have to get into any details of this equation, but that's electric force really, right? So it's again, it is the attractive or the repulsive forces between two electric charges. All right, so is that clear? The idea of magnetic and electric forces, or really non-contact force.
Yes, sir.
Okay, clear for everyone? All right. Okay, so then if it's clear, can you give me another example of a force which is a non-contact force? A very simple example, something that you would experience in your daily life. In fact,
Gravity.
there is no moment in your, yeah, exactly. So that's what I was
Gravity.
Gravity, right, exactly, right? So gravity is a force that you experience. There's no moment in your life that you would not experience gravity, really, right? So gravity is another example of a non-contact force, right? So that's gravity. And in very simple words, it is just the pull, right? So that's important. It is just the pull that is exerted by Earth, right? On any surface, on any object or anything, right? So for example, you know that, I'll give you a very simple example. I cannot draw an apple, but let's suppose that this is an apple, and the apple falls because it experiences this pull that is exerted by the surface of the Earth on this apple, and that's the weight of the apple, right? mg, right? And that's why it falls to the ground. Again, this is an outdated concept, but let's stick with it for now. I say it's outdated because we have a very better understanding of gravity. At this point, you cannot tell what is the reason, what is the source of this pull that this apple experiences, right? At this point,